Okay, let's get started. They're filming today for the OCW materials for Unified. So we're all going to be in a movie. No. We've got a challenging lecture today because probably the most complicated bit of work to do conceptually is our last lecture in propulsion. And the basic objective of that lecture is to, again, show how the moving blade rows in this engine can change the stagnation temperatures, change the stagnation pressures, and then connect that to cycle analysis, and then connect that up to mission performance. So this is the last bit. And I just want to point out in this picture up here, and when you look at this engine, the various things that you're looking at. So this engine, when it spins, you see the rotating blades, right? These are called rotors. So those are labeled with R's on that diagram. Now what you don't see, because they've been cut away and pulled off of this, are that between each one of those rotating blades, and if you look up in here, if you've got the right view, you can see it, or if you look over here, you can see them. In between each one of those rotating blades is a stationary set of blades called stators. Right, so that the construction of these is a rotating blade row, a stationary blade row, rotating, stationary, back and forth. And what we want to do is describe how that imparts power to the flow, or how you use that to extract power from the flow, as well. How does it change if you change the shape of the blades or the speed that the blades go? That's the last piece of the propulsion work. So we finished the first part of that in the last lecture, which was to talk about how you could have flow with one enthalpy coming in, some unsteady process, which is our moving blade rows, and then steady flow coming out with a different enthalpy. And we want to, again, look at the details of what happens in that box. That box here is drawn in a little bit more detail, where we now have the moving blade row here. And what we care about on this is the axial flux of angular momentum, because that's what's going to put the torque on the shaft, or that's what putting torque into the shaft with the turbine, which is the back part of this, does. It puts some torque on this, and then your flux of angular momentum, it's coming in. You have zero angular momentum coming into the engine, and these blades then cause it to have some angular momentum. Right? So it's the axial flux of angular momentum that relates to that torque. And then to connect that to the power, you multiply it by the rate at which you're doing work. So that's the rotational rate. And remember that these are vectors. So positive torque is a torque in the direction of rotation. Negative torque is a torque opposite to the direction of rotation. You then use the steady flow energy equation to connect that power to the change in enthalpy, total enthalpy. So that's mass flow times delta HT. And this is the part of it which is torque equal to flux, axial flux, that's the mass flow part. Angular momentum is the RVC, RVB, where V here is the tangential or circumferential component. You take change in enthalpy, equate it to change in the flux of angular momentum, and you're done. If you change the velocity tangentially with a blade row, and you have that blade row moving, you get a change in the stagnation temperature. Right? That's the enthalpy, C sub P delta T total. And so that's what we got to last lecture. Are there questions about that before we go on to the blades themselves? So key things to remember about this. we're going to be trying to solve for the change in tangential velocity in the rotating blade rows, because that'll give us the change in temperature across the blade row that would go into a cycle analysis. So we're looking for change in tangential velocity in the rotating blade rows. Now, first thing I have to do is show you the overall features of how the various exchange works. And I put this up last lecture as well, which is just another picture of the same thing, but it has the benefit of having the pressure and the velocity on it. So conceptually, what happens here is that the rotating blade row puts in some energy, then the stationary one converts that from swirling kinetic energy back into internal energy, and then I add some more with the next blade row, and then the stationary one converts it to internal, and then I add some more, and then another one converts it, etc. And you can see how many blade rows I might have. I could have 18 or 20 in a machine like this. And each time you're keeping the velocity pretty constant so that the axial component of kinetic energy through the machine is about the same. But you keep adding swirling components, convert that into internal. Add some more swirl, convert it to internal. Right? So let me put a few more words around that. And these charts will be available. I meant to have the handouts, and we had a printer problem this morning. So conceptually, the rotating part adds or removes energy. And it does this by changing the swirling component of kinetic energy and leaving the axial component about the same. And what I put down here is something that you'll recognize. What equation is that? The Bernoulli equation. All right, so this is one way you can think about the way this works. You can write the Bernoulli equation as having a component which is related to internal energy. Right? That's pressure, static temperature. And then three components of velocity. Right? I could break it up in any three vector components. So there's a radial kinetic energy, which doesn't change a lot as you go through this machine because it's in a pipe. So there's not a lot of radial motion of the flow. You've got the tangential component and the axial component, which again doesn't change a lot through the device. So what you do is the rotor puts in swirl, and then the stator, or the stationary part, converts that swirl into internal energy. And then the next rotor puts in more swirl, then the stator converts the swirl to internal energy. So what happens as you go through a device like this is that the velocity sort of goes up and down but stays about constant, and the pressure gradually gets higher and higher and higher until on the newest engines it may be 45 times the inlet pressure. Right, so very significant pressure and temperature increases. So again, rotors add tangential swirl, stators just convert it. How does a stator convert the energy? Yep. It redirects the flow. Remember this homework problem? Yeah. This is a stator. It's a set of blade rows that take flow that's coming in. If you think about this as the axial direction, or as the tangential direction, vertically here, and axial like this, it takes flow in and it changes the direction of it. Now, how many people here have trouble thinking about that as a stator? Does that make sense to you, or does it just look like a set of vanes, a set of airfoils? This is one of the difficulties that people have with this, which is why my daughter has been so kind as to make this for us, as I said. So I need to show you what it means to unwrap a compressor or unwrap a turbine. So you're going to have to be, imaginative about this. All right, this is this compressor. All right? Everyone see? Each one of these is a blade, and we're going to say that this set of blades is stationary, this set of blades is rotating, and this one's stationary. All right, so it looks a little bit like this, right? These are all at angles. The ones in between, it turns out, are at different angles. And it goes from what? 0 to 2 pi. Now I'm going to cut it and open it up. And now what I have is a bunch of blades that go from 0 to 2 pi, or an infinite row that's just stationary, and then an infinite row that's moving down or up. Right? This is the moving part. Right? Now, look at that picture. Each one of those blades at an angle in an infinite row is just a blade row. And that's what it means to unwrap a compressor. And we'll solve the problem in this sort of frame. Are there questions about that? Yes?
In that problem, aren't we saying that the streamlines are coming in kind of, well, because you even have velocity waves coming at the angle, but wouldn't it just be coming straight through?
It could be, but it turns out that if you have a lot of vanes, the flow tends to follow the vanes. Right? So that problem is a stator. So it's just a fixed set of vanes. So again, think about it like this. The flow's coming in straight. Now these vanes cause it to swirl, which is the same thing when you look at this of saying the flow comes in straight and then it goes in this direction.
But aren't we not saying it's coming in straight there?
Oh, yeah, it's coming in at an angle there. So it would be like saying it comes in at an angle and it changes its angle somewhat.
What causes it to come in at that initial angle?
Oh, maybe another set of blade rows in front of it? Right, so that's just a general problem. But the way that this then converts kinetic energy into internal energy, if you remember this, that the flow area coming into this was different, right? So you have a perpendicular distance across this pipe and a perpendicular distance across that pipe coming out, and they're different thickness pipes. So it's just like a nozzle. Right? A nozzle takes internal energy and converts it to kinetic energy. This does the same thing. You've got a small pipe, if you think about it, that gets to be a big pipe. Converts kinetic energy, lower speed flow, higher internal energy at the exit. So there are forces on these blades. There are torques, but they're not moving. So they don't do any work. They just take one kind of energy and turn it into another. Is that okay? Conceptually, you have to really be able to unwrap the compressor. So flow in this direction is tangential. Flow in this direction is axial. Questions? Yes?
That area looks like that area is bigger, so you're comparing that to a nozzle. So kinetic energy would be going up across that?
Oh no, since this is bigger, kinetic energy would go down. You'd have a lower speed flow at the exit of this than at the inlet. So this would be something, if you look at it, that takes some of the swirl, some of the tangential component of velocity, and converts it into higher static pressure, which is what stators do. There are also stators in the turbine that do the opposite. As you'd expect, compressors and stators are sort of mirror images of each other. One puts work in, the other takes work out. People all right with the setup for the problem? Because now we've got some rules, and we're just at the stage where it's useful for you to have the handouts, because I want you to draw on top of these handouts. So these are the charts that we'll pass around. So you'll have all these rules in front of you. I'll let you get the charts. Okay, that is an unwrapped set of blade rows, which is exactly what this green and pink and blue thing is. I've taken a set of blades and I've unwrapped them. And then what I did in that picture, to make it complicated, was I turned it like this. So you've got axial flow coming in the top, and then you've got that middle blade row moving in this direction. All right? So do you see how I got that? I took a set of blades and I opened them up like this. All right? This stuff on the right-hand side is what you have to learn how to do. And the whole purpose of these drawings is for you to determine what the tangential velocity is coming into the rotor and what the tangential velocity is coming out of the rotor. Because that's what goes into the Euler-Turbine equation. That's what tells you what the net flux of angular momentum is, if you know the change in tangential velocity. So again, this is axial. If I can write this better here. Axial. And this is tangential. So your purpose in this is to solve for VB and VC. Change in tangential velocity at the front of and the back of the moving blade row. Now, what are all the other lines here? These, the dashed lines, are what the flow velocities look like for someone who's sitting on the moving blades. And I warned you about this. The way you have to solve these problems is you go from stationary to rotating frame to stationary frame to rotating frame to stationary frame to rotating frame. So you have to do a transformation between those frames, between each and every blade row. Now luckily there's only one difference between the frames, and that's that one has tangential velocity, the other doesn't. So you don't have to do fancy, vector calculus to get between them. You just have to add this tangential velocity on and then remove it every time you go back and forth. Okay? Now there's a set of rules that we're going to follow. And I'm going to walk you through this, and then I've got two problems for you to do. There are two animated files on the web, and there's also a Java applet on the web that you can use to draw these. So there's a lot of things that you can use to drill yourself and practice on how to do it. These are the rules, and if you apply these, you'll be in good shape. And I'm going to work through and apply them once, and then you guys will do it twice on your own. Always consider a blade in a reference frame attached to the blade. So if you're in a stationary blade row, make sure you're in the stationary reference frame. If you're on a moving blade row, transform yourself into the rotating reference frame. That's why you have to change reference frames every blade row through the compressor. For unified, we're going to assume that axial velocity and radius are constant, which means that when you go back to the Euler-Turbine equation, I'm going to assume that this R is constant. RC is the same as RB. And there's no change in the axial component. So it just simplifies things. If you're going to do it formally for a real device, you wouldn't make that assumption. So this is just advice. Always consider the blade and the reference frame attached to the blade. This is an assumption that we're going to make. And then the rest are some rules. One rule is that the flow always leaves blades at the trailing edge angle. And you guys have had enough aerodynamics that you can tell me what's wrong with that statement. When does that not happen? So if this is my stall, someone mentioned, if this is my blade and the flow is coming in, it will tend to stick to this blade and head off in that direction. That's what produces the lift. I've got momentum coming in like this. I put the momentum down like that. I must get a force opposite to it. All right, so airfoils, and these are just spinning airfoils, change the direction of the flow, and that produces the forces. The only time that this does not hold is if you have stall and the flow separates from the blade. We're going to assume that this is a well-designed machine. You do get a lot of fancy kinds of stalls in these engines, but it's not the first thing you're going to try and solve. Right? So you're going to assume that the flow always leaves at the trailing edge angle. One of the things that's useful, and I'll show you in a minute, is that you're going to check the inlet flow angle to make sure that the flow coming into the blade is roughly aligned with the blade leading edge. If it's coming in like this, it usually means you have something wrong in your velocity triangles. Already mentioned this. You can only have work across the moving blade rows, so your whole objective is to find out what's the tangential component of velocity across the moving blade row. And that is in the stationary reference frame, that velocity. If you know the change in stationary reference frame tangential velocity and it increases in the direction of rotor motion, that means you've done work on it. You've added swirl. If it decreases in the direction of rotor motion, you've taken work out. You've taken swirl out. So the purpose of these rotating blades is to put in swirling kinetic energy so that the stationary ones can convert it into internal energy, and you go on and on and on. All right, before I go ahead and do an example, questions about that stuff? Yes?
Actually, kind of the same question from before with that diagram. The trailing edges don't.
This diagram?
Yeah. Are we going through this from top to bottom?
Yep. You will go through from top to bottom. This is the front of the engine. This is the back of the engine.
When you come off the guide base, isn't the flow going down into the right?
Yes, it is.
So then, how's it?
You're going to see that. It happens to line up exactly with these blades when you're in the reference frame of those blades. So for this little person sitting on the blades, this looks just fine. And that's what I've got to show you. That's how you're going to follow these rules. Right?
And do you end up with shocks in between those?
We're going to assume that this is shock-free, largely incompressible flow for the purposes of unified. These things do spin with tip Mach numbers of 0.8 or 1 or 1.2, and you do get a lot of compressible flow effects, but we're not going to address them. Okay, now I want you to do the same things that I do on your handouts. Okay? We're going to follow these rules. The first thing that we said to do is check the incoming angle of attack of the flow. So from the perspective of an airfoil, this would be the angle of attack on that airfoil, right? You have to, put yourself in the frame of reference of sitting on an airplane's wing here. So if the higher the alpha here, the higher the angle of attack. But that's reasonable. You'd expect to have a positive angle of attack coming into these blades. Okay? If it were negative, you might worry a little bit that something was wrong. The next rule is assume that the flow always leaves the blade at the trailing edge angle, which is this. That is this vector right here. That is VB, or big VB, which is the total velocity, and little v is the tangential component of that. Right? So you've just solved part of the problem. You just found the tangential component of the velocity in the stationary reference frame coming into the rotor. It's this little green arrow right here. Can people see that okay? That's sort of the easy part. You haven't gotten to a moving blade row yet. Now, this does not look good, right, to have flow coming into this blade and it's almost perpendicular to it. When you transform to the reference frame of this rotor, you'll see that it lines up with it beautifully. And the way you transform to the reference frame of this rotor is you take this velocity and you now add, depending on your sort of frame of reference, subtract the speed of the reference frame. So yeah, unclear. My apologies. If you are in this reference frame and you want to transform it to the reference frame of someone sitting on these blades, you need to take account of the speed of this reference frame with respect to that one. So this reference frame is moving past this one in this direction at omega r, or from this perspective, this one's moving past this one in this direction. That was a lot of thises in that statement. Let me finish the vector addition here, and then we'll talk about it. So if I add the stationary frame flow vector to the omega r that gets me to the rotating frame, I then end up with, I'll try and be consistent here, the relative frame velocity, which you can see lines up nicely with these blades. So we've just done a frame change. Now, it makes sense because it lines up with the blades, and I told you it ought to roughly line up with the blades. Does it make sense to you conceptually? No. Think about having the flow coming in straight to these blades into the rotor. So look at the case where the flow comes into them straight, and assume they're not moving. Then you just see the flow coming straight at you. Now assume you start to move in this direction. Which way do you feel the wind blowing on your face? So you start to move in this direction then. You start to feel the wind on your face in this direction, right? If you're sitting here on the blade. You start moving this direction. So just think about it. I'm the rotating blade, right? I'm sitting here, and the flow's coming straight at me, and I start to move, right? So I'm going to start to feel flow coming at me this way, opposite to my direction of motion. Right? So that's exactly what you see up here as these blades start to move in this direction. This flow vector, which was initially like this, turns around and starts blowing for the person sitting on these blades opposite to the direction of motion. So conceptually, that ought to make sense to you if you think about yourself sitting on these blades. Does that help? Some yes, some no. Some. All right. Now you're almost done. in the reference frame of this blade now, you assume that it leaves at the flow angle, or at the trailing edge angle. That is this, which I keep drawing in red to stay consistent over here. So that's the flow angle leaving these blades. And now, what I really care about again is this component in the stationary frame. So how do I get back to the stationary frame? I add omega r, which is, if I've got a pen here, I add omega r, I don't have the right color pen, which is this black line on the bottom, to this red vector, and now I'm back to the stationary frame. And the component of that I care about is the tangential component, which is that little green vector along the bottom. Yep.
Looks like before we had primes as our exit part, and the
Nope.
non-prime is our entry.
Now, let me now explain the nomenclature, which I wanted to stay away from a little bit on this. The A, the B, and the C are for whether you're upstream of this blade row, this one, or this one. So that's what the subscripts are. The primes mean that you're in the relative frame. So this is the relative frame velocity. And the unprimed means you're in the stationary frame. That's what the symbols mean. I wanted to sort of stay away from the symbols for starters. So this is complicated. You're going to work a problem on this in a moment. Let me just go through the steps again. You assume the flow leaves the trailing edge at the trailing edge angle. So that gives you this vector. Basically, this flow is turned or added some swirl, but since it's not moving, it's not done any work. It's just converted internal energy to kinetic energy. I then put myself in the reference frame of the moving blade by subtracting its velocity, and that gives me the red vector, which the person on the blade would see. I then say, well, the flow will always leave this blade attached to the blade at the trailing edge angle. So that blue vector then, which I should have drawn as red here in the relative frame, I'll draw it on this one. My pens work. That vector is this one. Then what I care about is this tangential component of the stationary frame velocity. So I add back on, to get back to the stationary frame, I add back on the rotating component. I get the total flow vector, which you now see has more swirl. So this is a compressor. It's added swirling kinetic energy to the flow. Yeah?
For B prime and C prime, they leave at the same angle? That same angle?
B prime and C prime, those are different. It comes in at this angle and leaves at a little bit different angle. These blades don't have a lot of turning in them, but you'll see there's a little, right? It goes from this to this.
Right. More work is done on them over the stator.
There is no work done over the stator. There are forces, but since it's not a moving blade row, those torques, there's no rate of applying the torque, so there's no power added to the flow. They just change the direction. So you get forces, and you calculate those in homework, but since it's not a moving blade row, no power added. Right. This is a lot of sort of complex ideas all at once, and the only way to do it is to practice it. Okay? And the rules will be good to you. If you follow the rules and you work your way through these blade rows, you will end up with being able to do this kind of analysis. So what I've got here are two problems, and the first one only has two blade rows on it. I'll hand it out so that you can draw on it, since that's sometimes helpful, and I'll put it up here as well. Let me first show you the problem. These are two blade rows. This one is stationary. This one's moving. And I want to know, is it a compressor or a turbine? How do you know if it's a compressor or a turbine? A compressor puts in swirl in the direction of rotor motion. A turbine takes it out in the direction of rotor motion. So you need to do the velocity triangles on this and just follow your way through the rules. So let me hand out these. Carl, do you want to help me? And you can draw right on top of them, as I said.
Swirls got to come from actually, or around here tangentially.
Oh, hang on. Pass one.
So what should,
How did you assign values to like omega r as far as length? Will those be given to us?
Oh yeah, I will draw them here. One of the important things about this is to actually draw it to scale, or else you can get some funny answers. Right, right. Yeah, there was just a good question here. When you draw these, it's important when you draw the triangles that the length of the vectors be right. So if I've here drawn omega r as this long and w axial as this long, it's important to draw them those lengths, right? Or your triangles will come out misshapen and you can make the wrong conclusion. So you need to be neat about it. In other words, you can draw it right on top of these three vectors. You can start your triangles right on top of these. Oh, I'd give them 3 or 4 minutes at least to go through this. Draw it right on top of this so that it's to scale. Yeah, the triangle. So, you know, here, for example, you could say, well, the flow coming out of this stationary blade row looks like this, right? Because it's got to have this length, and it's got to have this angle. And then subtract off this, that same length. Yeah. And then this would be sort of the relative frame, 1. Okay, so this is what I mean by draw it right on top of it like that, all right? Yep.
If we're assuming that this is properly designed, something, do we only have to look at the end?
You need the change across this. You need the inlet and the outlet.
We're not looking at the total change from axial to...
Well, yep, but there is a conversion between these two. So this converts energy, and then this adds it. So if you want to know the total amount added, you have to know the inlet and the outlet for this, because this puts in some tangential velocity you can sort of see here, but it doesn't add any energy. And what you want to know is how much energy is added or taken away.
Isn't that just a function of this difference in angle in this?
it's a function of the difference in tangential velocity here versus here in the stationary frame. So go ahead and draw the triangles.
And then we'll have this going like that. That's going to have
Even more.
an instance. It's going to give it more.
Yeah, yeah, but you need to draw them out.
Okay.
Oh, this is good. Draw it right on top of here.
Oh, okay, just to get the
Yeah,
scale.
well, that way you get, you can say, hey, this angle is exactly this angle.
Okay,
And then you can say, well, I'm going to add this vector on to here,
okay.
and that gives you this sort of one in the relative frame. So just keep these lengths all right. It's easier to just draw them right on top of that. This looks good, really good. Yeah, so this one, the flow coming in, is just coming in straight. So then what you want to do is say, well, the flow's leaving these blades at this angle. And then you want to subtract this to get into this blade's reference frame. So go all the way out to here, which is roughly what you did. Yeah, give us another minute or two at least, Carl. And then this is the relative one. And same thing. This is now the relative angle. It's the angle that comes off the blade. So you need to then get back to this. And then you want to look in this for what's the tangential component.
It's really easy to draw right on top of those vectors like that. Oh, right. Keep it straight.
How you doing?
You've got the right thing here, but sort of, as long as you can do it to scale in your head, you're okay. As long as you draw it right on top of the vectors, then you don't get anything messed up. More time? Or?
No, this is good. People are on top of this, actually. All right, get your answers in. I've walked around, and more than half of you appear to have this well in hand, which will mean that we may have just enough time to do another one. And if not, we'll have plenty of opportunity with homeworks and recitations to go through more examples of this. So get your answers in, and then I'll work through it up here. Okay, so most people picked a compressor. If you did, that's the right answer. I hope you got to it for the right reason. I was actually, have to say, impressed walking around here that most of you went ahead and did this quite well. And it is challenging because you've got to think about unwrapping the compressor and thinking about things rotating, and now instead they're going from left to right, and you've got to work your way through all the frame changes. But most of you were on top of it, which is good. Right, so just follow the rules. So let me sort of show you how to do this. I wish I had a little bit thicker pens, but I think you'll be able to follow along. So first, this is the whole velocity vector coming into this blade row. There's nothing more. It's pure axial flow coming in. And then I say the flow leaves that stationary blade row at this angle beta B. So that's beta B. And then I need to put it in the reference frame of the rotor. So I subtract the rotor velocity. And that then gives me in the axial, or in the rotating reference frame the velocity coming into this blade row. And it looks about right. It's roughly lined up with the leading edge on those airfoils. So that's good. Then, and this gives me one very important thing, I also have the tangential component here in green of velocity in the stationary reference frame coming into the rotor. Now I do the same thing at the back of this, but now I'm in the rotating reference frame. So I've got velocity leaving this, following the blade angle. I then add back in this velocity to get me back to the stationary frame. That gives me my stationary frame vector. I look for the tangential component of that, which is this part. And I say that the tangential component has increased across the blade row, where increase is measured in the direction of rotation. Therefore, it's a compressor. Questions about that? Yes?
Can you also look at that as the tangential components going that way, meaning the work is going downstream?
Well, again, the point of these is that they take a flux, which is the axial component of the flow, of angular momentum and change it. And the angular momentum here is, in the direction of rotor motion. So again, I would just think about yourself as a fluid particle, and you're traveling through this engine, right? And you come in and you've got no angular momentum, and then whammo, you hit these blade rows, right? And now your flux of angular momentum is changed. You have some positive flux of swirl going through the engine, and each one of these blade rows keeps changing that as you go through. Right? And it's only the moving ones that add the energy. The stationary ones just convert it from swirl back into the axial direction, and in doing that, convert it to internal energy. Okay? How are we on time? We are at the about 3 minutes to go before the end here. There's another problem that I had hoped to get to here, and I want to show you just the animated image for it. Can you run the Q30 one? No, not that one. Well, first, if you look on the web page, there's an interactive program that you can use for drawing velocity triangles that a student from Unified wrote. It's a little Java applet. And where's the GIF on here? I bet you I can find it. Yeah, hang on. And this is the second problem. And you don't see the whole thing up here, but this is a graphical image that you can click on. It'll go through and it'll draw each of the vectors for you. All right, so the answer for these, as you can see here, is animated. So you can go ahead and try this. The other one that we just did is also animated. So if you have some questions about what I've done here, you can go through and follow it and make sure you're following the rules. Right? So there are a couple resources there to help you if you're confused, and I can always help you. All right? So that's just to point you to the resources. Again, about a week and a half from now, we will have the propulsion quiz. There will be a question much like this one that you just solved on the quiz, where you have to draw, 2 or 3 velocity triangles and identify, is work being put in or taken out. Right, so this is something I want you to practice, and it's nice because it achieves the objectives of getting you all the way from details of blade shapes all the way up to mission performance. And you've got a homework problem on this engine too, where I ask you to go and measure the angles on the engine and tell me how fast the blades spin. So do it in reverse. Here I've told you how fast they spin and given you the angles and asked for the work. Instead, I'm going to have you measure the angles and based on this kind of analysis determine how fast they must be spinning. Okay? Questions before we wrap up? Yeah?
When they're actually designing these things, which do they decide first? Is rotor speed or is the shape of the blade?
The question was, when they're actually designing these things, what do they decide first, the rotor speed or the shape of the blade? The answer is yes. You start out with a cycle analysis for this, so you determine how much pressure you need. Then you look back at your old engines and you say, well, for each one of these blade rows, how much pressure rise was I able to produce? And you know what those shapes used to be. And you know how fast you spun those blades as well. And how fast you spin them is tied to your structural capabilities of the materials. And then what you typically do when you design, you say, well, I'm going to try and spin it a little faster or push that a little more. Or maybe I'll turn the flow a little bit more than I did in the past so I could eke out a little bit more pressure rise per blade row. And if I'm really good and I do that for all my blade rows, maybe I don't have to carry around one of these back stages anymore. And now I shorten the whole engine. It gets lighter, improves my range. So you do it all at once, but with some knowledge of what you've done in the past. Yeah?
How much of this is just try it and see if it works, and then if it works, improve it a little bit? Or?
How much is try it and see if it works, and then if it works, improve it a little bit? Very little these days, because you have a lot of advanced computational tools to help you design each and every aspect of this. And it costs you $1 million a day to test one of these. So you just don't have, and to build it, each one of these turbine blades may be $5,000. You just don't have all the money to just test it and try it and see if it works. You've sort of got to go from fundamentals and design it.
What sort of tools? Is it software tools? Or?
Yeah, it's software tools that take equations like these that we've worked with and solve them for each small particle of flow. Right, and add them all up and integrate them all. All right, please fill out your muddiest part of the lecture cards. I will respond to those. I get on an airplane tonight, so until I sort of land on the ground back there, I won't have them all posted up, but I will endeavor to do that. And I think we've got one more recitation before the quiz. All right? Thanks.